So let's talk about the attention mechanism. A very important neural network unit, the core unit of transformers, foundation models. These are state-of-the-art models for text and then images and structured data. Of course, what we learn in this course, very important mechanism. Some context before that. Originally, the attention was proposed for language translation, French to English, English to French, and then it was used and highlighted and basically got its prestige from the seminal paper, Attention is All You Need. This paper introduced the transformers for natural language processing, and there the attention is a core unit. The core of the transformers, as we'll see, is the attention. Okay. Now, in time, it was adopted by other modalities. Again, images and also the structures that we care about, tables, graphs, relational databases. We'll see table usage of attention or transformers, and then later in the course, we'll see them in graphs and relational databases. Okay. Now, the attention is useful because it seems to provide high capacity, okay, high flexibility that is able to provide nuanced observations, okay, from the input to the output, rich flow of information while still being simple enough to be learnable, okay? And that's what makes them so important for things like the foundation models, like LLMs that we are seeing today. It is really a revolution, the attention mechanism, okay? So I'm going to explain it in a simpler abstraction, not the usual context of a text, and because in the context of text, there are some complexities, specifically the position or the location of a token in the text that you incorporate in the original transformer, and that complicates the presentation, while the core of the idea, is something that you can understand without the position. And also, this is not important for the case of structured data that we care about in the course, so I don't account for the position. I take a simpler view. And this simpler view, you can understand it through the following analogy. So we have this person here, this lady, who is interested in getting expert opinions, the opinions of the experts on her offering. Say she wants to interview for a job, okay? So she goes to them and they give her opinions about her, but everyone is an expert on different fields. Okay, one is an expert on CVs and presentation, and one will give her comments on her cooking and presentation. And in the end, she wants to get this score of greatness, coolness, mastery, and everyone will give her these three scores, but based on their expertise. Now, she's interested in specific things. Okay, the CV, the math skills, and her presentation skills. And so she's going to aggregate her opinion, the opinions of the experts based on what she cares about. So what she cares about is the query, is what we'll call the query. What every expert has to offer, the expertise of the expert, is the key. And what you basically aggregate in the end is the value. Everyone comes with a value, and then you're building an aggregated value. A different context. So we have an observer, X, and we have context items, C1 to Cm. Okay? Each Ci has a value, Vi. We would like to summarize all of the context values Vi into a single vector, V hat, summarizing the context. Okay? Now, one thing we can do is just take the average, but we're looking at a situation where not all of the context items matter to every X, but every X should combine, aggregate, account for the information of the context items differently. So we want X to pay attention or to learn how to pay attention to different elements of the context items. So instead of taking an average, a simple average, we take a weighted average, okay? But not fixed weights. We actually want the weights to be such that we learn. X learns what it cares about. The context items learn what they have to offer. Combine the query with the key, okay, the query of the observer with the key of the context, and that will give you the weight in the weighted average, okay? So we learn a query, that's the interest of the observer. We learn a key, that's the offering of the context item. And combining them, we get the weight that we want for the context item, for the value of the context item. Now, in effect, the query and the key are vectors, and the combination of them is just a dot product of them. And then what do we do with this dot product? When we want to construct a normalized vector out of them, a probability distribution, we do the usual thing, softmax. So the attention definition is just a direct translation of this intuition into formulas. We have this Q, which is the query of the observer, vector in the K, okay, and the different keys. Okay, every key is a vector of length dk. We have M observers. Each observer has a value of length dv. Okay, so then the attention formula is really just what we said. You take the query, you multiply it by the different keys. Okay, you get different numbers. You scale them by a number that is chosen to be, the square root of the dimension of the queries. No fancy explanation for that I'm aware of. This gives you numbers. You construct a weighted average and normalize the distribution out of that using softmax. And this gives you the weights that you use for combining the values. And so you get a weighted average of the V matrix, okay? Now, usually you don't have one observer, but a list of observers or a sequence of observers. So it's not one small Q, but rather a matrix of N Qs. So the formula looks like the observer matrix Q multiplied by the keys, transform, scaled, then softmax, then multiplied with the values. And this is how it is illustrated in the transformer. Is all you need. Paper, exactly what we described, except for the masking, which I didn't mention here. I'll say something about it later. Okay. Now, to enrich or to strengthen the effect of the attention, we use multiple attentions, okay? They perform independently and we combine them together. Just amplifies the strength, the ability of the attention, okay? Each one of these is called an attention head. We apply them independently. Each we can scale with a specific matrix, okay? Then we concatenate them and somehow combine them using, say, a linear model to match with whatever output dimension that we want. Okay? So this is how it looks like. You take a concatenation. The multi-head of Q, K, and V is a concatenation of different attentions. Each attention is a Qi, Ki, Vi, which is Q, K, and V multiply by corresponding matrices for that head. Every head has its own separate matrix of weights, and of course you need to adjust the dimensions. Okay, and in the end you apply the final transformation WO to get whatever dimension that you want. Okay, and yeah, note that I'm using this dotted circle to denote not just concatenation of vectors as we usually do, but concatenation of matrices, which is the same. Just place B to the right of A. Okay, now one important distinction between the different usage of attention is relates to who attends to who. Specifically, where are these K, Q, and V coming from? Now, the way I described it, you have like two types of objects: the observers X and the context items C. Okay, and they are represented typically as matrices. And so, to get the queries, the keys, and the values, you take the X and V or X and C and scale them by some matrices. Okay, or transform it, apply some linear transformation. So Q corresponds to the observers multiplied by some matrix WQ, and then K and V are obtained from C by multiplying it with matrices. Okay, now two important scenarios. Cross attention is basically the case where the observers and the context items come from different worlds. For example, you can have an image or a textual question about an image, and then the text tokens are attending to the image pixels or the image blocks. Okay, or you can have the English tokens attending to the French tokens. Okay, so that's cross attention. The attention is from one set to another. And then there is self attention, where the same set, X and C are the same, X equals C. And basically, then you have a collection of observers attending to each other. Okay, so the observers are the context of themselves. Self attention is very commonly used. Okay, so transformer is basically obtained from the attention by several layers. You have an input encoding, and then you have the attention, multi-head attention, each followed by a feed-forward network. And then you take the stack of multi-head and feed-forward, and well, you also use skip connection. I'll say something about it next. And you apply several of them, n layers of this combination of multi-head attention and feed forward. Finally, apply a decision layer, okay, which is usually a simple feed forward or linear layer, and it is followed by softmax. Okay, so transformer is really designed for multi-class classification. Okay, because in the end, when you apply softmax, you get a distribution among n items, okay, the dimension of the softmax. It's really a different distribution between a finite fixed set of items, okay, and this is what we see here in the transformer, okay, and so what is going on here? We have the inputs, that's the prompt, and we have the outputs, that's the proposed continuation of the prompt. Okay, we have their embeddings. We have the positional encoding that we basically ignore, but this is just encoding the position of the tokens in the text. And then what we see are layers where we apply self-attention, multi-head attention between the inputs. Okay, now this is the skip connection. We don't use directly the multi-head attention, just the result of the multi-head attention, but we also combine it with the input. We add the source input directly plus the result of the multi-head attention and normalize. That's a skip connection. Okay, this is very useful to avoid learning anomalies. Once we apply this multi-head attention, we apply a feed forward, and that gives us one layer. Okay, and we also have a corresponding activity in the output tokens. Okay, to apply against self attention. Here we use masked attention. Now, I'll just say briefly what is this masking doing. It assures that the token is attending to the previous tokens and not to the future tokens. That's what it does. And then you apply a again, skip connection. Then you combine basically the input elements. So you attend also to the input input elements. Okay, so this is cross attention between the output elements and the input elements. And again, feed forward with the skip connections and so on. And all of that happens n times, n layers of that. Okay, after you're doing all of that, in the end, you make the decision. A linear layer followed by softmax. Okay, and then you get a distribution between categories. That's the transformer. An example of using the transformer or adapting the transformer to our context is tab transformer. Basically using the transformer for tabular learning. What did they try to solve? Well, basically they wanted to use the transformer to properly handle categorical values in tables. Okay, basically simulating the fact that categories they are not independent. There are intricate correlations between them, and we want the categories, the different values of the attributes to attend to each other to help us making a good decision in the end. So this is what we obtain. You see here, you have the categorical features of the row, okay, and here you have the numerical feature of the rows. This one gives more information, okay. The representations have parameters. The numerical, we scale them and so on. Now, with the categorical features, you have here M attributes, categorical features. We combine them using something like the transformer, multi-head attention, skip connection, feed forward, skip connection, okay? And we apply it n times, like the transformers and layers of that. The feed forward is a very simple layer, which is basically linear with one value involved. Okay, value of x plus bias times another matrix plus another bias. Okay, that's the feed forward. Okay, now you take whatever you got from the transformer of the categorical attributes, whatever you got from the scaling of the numerical attributes, you concatenate all of them, and then you make a decision, okay, which is just a multi-layer perceptron, and they try with 1 to 12 layers, which in the end gives you a loss function, okay, and they ran the experiments, and they show something interesting that what we see here is that on different classification tasks, okay, binary classification tasks, and the fact that they use the classification tasks also explains why in the end they didn't use a softmax, but really a loss that gives you one probability. And you can see that basically the leading models our tab transformer with all of the fanciness of the transformer model, and also the decision tree. Okay, gradient boosted, XGBoost. Okay, so in some of these tasks, XGBoost is the winner. In others, a tab transformer. Okay, so this is interesting to see that.